Hello and welcome to this lesson on interpreting scatter plots. So this is the next stage in our scatter plots. In the previous lesson we learned how to describe scatter plots using positive, negative, linear, nonlinear, or no correlation. We also learned how to make scatter plots from a table and plotting our points and making scales and labels and that kind of stuff. In this lesson our goal is going to be, given a scatter plot, if we are given one, can we answer some questions about it? Can we make some predictions from it? Can we come up with equations for line of best fit and things like that? So this intro question says, how do I interpret scatter plots? Our warm-up says, scatter plots are used a lot outside of school. How do you think scatter plots are used outside of a school setting? And they're used quite a bit of places. They're used a lot of times in business. They're used in science a lot. If scientists are determining if like a drug helps lower blood pressure, they will give people this drug, or they'll start with animals first, and they'll give animals this drug and record how much of the drug they gave and how much it lowers the blood pressure, and they can use that, and say, okay, well, if we gave this much drug and their blood pressure is here, then we gave more drug, now their blood pressure is there, and they gave more blood or more of the drug and their blood pressure is here, they can say, ooh, look, there's a correlation here. There's a connection between these variables, that the more of this drug we give, the more the blood pressure goes down. So that's a way that it's used a lot outside of school. The two vocabulary words here are the same words we had in the previous lesson. It's scatterplot, which is just a way of displaying bivariate data, and the line of best fit is a line that attempts to model the data. And we did some practice drawing these lines of best fit in the previous lesson. So here in this first problem, it says, the graph below shows a scatter plot of a research study at a middle school comparing the hours of sleep each night and the students' achievement. So their achievement would be like their grade and versus how much sleep they get. The line of best fit is already drawn for the data. There it is. Write the equation of the line of best fit. Okay, so that's fairly straightforward. So our job is to write the equation of this line. So we're going to be using our slope-intercept form, which, in case you don't remember, is y equals mx plus b, where that is our slope, and that is our y-intercept. So looking at our data and looking at our line of best fit, our line goes through, well, I'm going to try to find a couple points. So it looks like it goes through here and there, and actually goes right up this diagonal. The slope appears to be up 1 over 1, up 1 over 1, up 1 over 1, and that pattern continues. But I'm going to remind you that this slope is not 1 over 1. We talked about this when we were doing functions, that you have to pay attention to the scale as much as the boxes. So like this up 1 box is not up 1 unit. The y-axis is counting by 10, counting by tens. 0, 10, 20, 30, 40. So this is actually up 10 over, and this is over 1, from 1 to 2. So up 10 over 1, up 10 over 1, up 10 over 1. So my slope is y equals 10x. And then my y-intercept. My line, the line of best fit, is crossing the y-axis at 0. So I don't need to put a little ghost 0. You can if it makes you feel good. This is the equation you would see in a textbook, in an answer key. They're not going to have a plus 0 there. But I want you to understand that that is there. It's the ghost, it's the y-intercept. Okay? So, write the equation of the line. We did. Y equals 10x. On average, how many hours of sleep would a person need to get each night if they wanted to get a 90%? Well, now that we have our equation, this is pretty easy. Now, we could answer this from the graph, but with an equation, check this out. I'm going to plug 90% in for the percent variable. Now, sleep is my x variable, and the grade is my y variable. So I'm going to plug 90% in for my grade variable, the y. And if I solve this little equation just by dividing by 10, get the x by itself, divide by 10 on both sides, we get x equals 9. So they would need to get 9 hours of sleep in order to get a 90%. That's based off the equation. Based off the picture, we can see that is also right here. There's the 90%. There's the line, and that happens at 9 hours of sleep. Okay, both ways are good. What does the slope of the line mean in terms of a given scenario? Hint, interpret the slope as a unit rate. So the slope here, the slope is 10. And previously we had that as like 10 over 1. So what does that slope mean in the scenario of like the people sleeping and their grade? How does it matter? Well, that slope of 10 over 1, if you remember when you found the slope, it's always like rise over run. That is your y variable over the x variable, right? The rise is the up and down. That's your y variable. The run is the sideways. So if I start throwing units back on here to make sense of this 10 over 1, this would be 10 grade, or percent, over 1 hour of sleep. So now I can make sense of this. I mean, 10% for 1 hour of sleep, meaning every additional hour of sleep you get, your grade goes up by 10%. If this was a negative, your grade would be going down by 10%. So, and I'm not going to write this because you don't need to see me write a sentence, but each 1 hour of sleep you get, or each additional hour of sleep, your grade goes up by 10%. That is what the slope means in this problem. That's what this 10 is representing. Okay. If you want to pause the video and rewind that to write yourself down an answer, you can do that. I'm not going to write this though. Letter B. The graph below shows the years of education and income of people based on data collected by the IRS. So here is this beautiful data. The line of best fit would go through the points, boom, boom, and boom, boom. Find the equation of the line of best fit. Okay, so you should be able to do this. So I'm going to challenge you. Could you right now pause the video and find the equation of the line of best fit? If you get stuck, you need a little help, or when you're done, hit play and we'll start going through it together. All right, so the first thing I would do is I would actually graph the points they have here. So 1 and 16, or 9 and 1600 would be here. In my scale, they're counting by 400s. 12, that would be 1600, 2000, 24, 28, 32, 36. Okay, so there's the first point. And then 15 and 3600 would be right there. And then I could draw my line. And I'm even going to draw my line in reverse. So there's my line. And now I can find my slope, because in order to write the equation of the line in best fit, I need my slope and my intercept. And I can find the slope from the pretty picture. I can go, you know what? I'm just going to go straight up to here and over to here. This is up, well, from 1600 to 3600. That's up 2,000 units from 16 to 3600. By the way, what we're doing here is essentially the slope formula. We're taking y2 minus y1. 3600 minus 1600 is 2000. Going from 9 to 15, that is a change of 6 units. 15 minus 9 is 6. So my slope could be simplified as, or written as, 2000 over 6. I bet you 2000 over 6 simplifies. I know it does, because they're both even numbers. Simp equals, and that does not simplify anymore. So my slope is going to be 333 and 1/3 x. Now, the hard part about this problem was actually the y-intercept. I believed everybody here could find the slope, either using the 2 points using the slope formula, which I didn't actually write. Here, I'll write the whole slope formula in case you need it or missed it or forgot it or don't remember it. M equals y2 minus y1 over x2 minus x1. So you could have used these 2 points, plugged the values into the slope formula to find the slope. It would be the exact same thing we got. But when you're finding the y-intercept, this problem becomes a little bit tricky. You cannot trust the graph. If you took a guess and you said, oh, this y-intercept is like 900. I mean, it looks like it. I mean, it's less than 1200, not quite down to 800, so 900 or 1000, something like that. You would be actually quite far off because of these little symbols right here. This little symbol here is called a break in the scale. So if you'll notice, I mean, the origin is always 0, but we've essentially skipped all the numbers from 0 up to 7. We've skipped all of these numbers in this little break, and then we've just kept counting by ones. On the y-axis, we skipped all the numbers from 0 up to 800, and then we were counting by 400s. So what that ends up doing for us is making it so we can't trust where it looks like this line is crossing the y-axis. The only method we have now to find our y-intercept, and you'll notice we actually have workspace because we're going to need it. The only method we have now to find our y-intercept is by plugging in our slope, an x value, and a y value, and finding the b. We did this in a previous lesson on finding the equation of a line. So that would be, I'm going to take this equation here. I'm going to plug in these points. This point right here, the 9 and 1600, because the number's a little bit smaller than this one. So I'm going to plug the x value for x. So that's become 333 and 1/3 times by 9. And I'm going to plug the y value in for the y. And when I solve this equation, I will find what my b is. I will find the y-intercept. And I'm guessing most of you did not go through this process. You probably took a guess or an estimate, or you just simply didn't know. So now that I've hinted you on what to do and I've kind of set it up for you, I would encourage you to pause the video and see if you can work through this process and finish writing the equation of the line. If you did do this already, well, let's keep going. So I'm going to take that 333 and 1/3 and multiply by 9. So that number is now 3,000. And I'm going to subtract 3,000 on both sides, and b equals, it's going to be a negative 1,400. I bet nobody would have guessed that that's going to cross at a negative 1,400. But it does. So the final equation of this line is y equals 333 and 1/3 x minus 1,400. Okay, that's part of interpreting the line of best fit, and interpreting the scatter plot is being able to come up with this equation. And we have experience writing equations of lines, just not in this context, which is why we're doing it this way. All right. Based on your model, which is the equation that we made, what is the income of a person who went to college for 2 years expected to make per month? All right, well, now that we have this equation, this problem actually becomes fairly simple. I'm going to copy this and paste and get rid of some of the junk. So all we have to do is plug in the right number of years in for the years variable. Now you may be going, well, which x or y, which one is the years variable? And if you don't know, look at the graph. Which one's on the x-axis? Or which one is the years axis, I should say? The years axis is this x one. So we're going to plug in the years for the x variable. But how many years of education would 2 years of college be? Question was, the income of a person who went to college for 2 years. If I plugged in a 2 right here, that would not be college for 2 years. That would be a person who got 2 years of education. They dropped out in 2nd grade or finished 2nd grade and then stopped. Okay, we want 2 years of college. So let's think about this. You graduate high school in 12 years of education. 2 more years would be a total of 14 years of education. And now this problem just became punching buttons on a calculator. We did the problem solving, we did the thinking, now it's punching buttons. So 333 and 1/3 times 14 minus 1400 equals, I would expect that person to make about 3,266.6 repeated dollars per month. Now, if your calculator does not have the fraction unit rate button like we did, another way I like to do this is I'll just put in 333 point, and I'll fill the screen with a bunch of 3s. That will give us a good enough answer. Times by 14 equals minus 1400. And look how close our answer is. 3266.6 repeated, 3266 point, and it looks like 6 repeated. Okay, so that's something you could do even with a non-fancy calculator. The next question says, how much more a year would a college graduate of 16 years, that would be a bachelor's degree, 16 years of education, not 16 years of college, 16 years of education. How much more a year would that person make than an 8th grade dropout? I'm going to have you try this problem. So you can use the same equation, you can use the graph above if you want to. How much more a year would somebody who graduated college with a bachelor's degree, which is 16 years of education, how much more would they make than an 8th grade dropout? Pause the video, try this one on your own, and when you're ready to continue, hit play, and we'll go through it together. All right, now, I'm going to use the equation because equations are much, much, much more accurate than my graph. My graph, I would be estimating, like 16 years, I would be estimating whatever this number is. I don't know. 8 years, I'd be estimating what that number is. I don't know it exactly. But with my equation, all I have to do is take this same equation, plug in 16 years of education, plug in 8 years of education, and then punch the numbers in the calculator. It's much, much simpler. It might be a little bit more writing, but it is a whole lot simpler. 333 and 1/3 times by 16 years of education minus 1400. And then I'm just going to type the buttons in the calc right now. 333 point times by 16 minus 1400 equals. So a person who went to college and graduated college, I would expect to make 3,933.3 repeated dollars per month. Okay. 8th grade dropout time, 333 and 1/3 times by 8 years of education minus 1400 gives me times by 8 years of education minus the 1400, and that gives us y equals 1266.6 repeated. Again, I'm assuming it's repeated, but this 4 here is because we didn't use the 1/3, we just used a bunch of 3s. This probably would keep going 66666 if we repeated. So that's how much money a college graduate makes. That's how much money an 8th grade dropout makes per month. Now, the question was, how much more a year would a college graduate make than an 8th grade dropout? So we need to find a difference of how much money they make in a year. Okay, so I'm going to take their numbers here, and I'm going to change this. This is a month per month. And to make it per year, I'm just going to simply multiply it by 12. This person times by 12 makes $15,199.99 a year. So essentially $15,200 a year. And actually, rounding that, we probably should actually round that up. There. My eighth grade, or my college graduate, 3933 times by 12 gives us equal, actually it's not Y. Get out of here, virus definitions. What do we get? So times by 12 gives us 47,200 a year. And then finally, our last calculation is just how much more. Okay, so I'm going to take the college graduate and subtract by the 8th grade dropout, and we get a difference of $32,000 on the nose. So per year, it's expected that a college graduate with a bachelor's degree would make about $32,000 more a year than an 8th grade dropout. Okay? And all of that information we got from our equation. Once we knew the equation of the line, we could then plug in whatever number we want in here for our years, and it'll tell us how much education they give. We want to know how much money would a doctor make? Somebody who went to college for, 8 years. I could figure that out. 333 times by, 8 years, past 12 would be 20 years of education. Oh, look at that, my 3 disappeared. That's interesting. Whatever. Minus 1,400 gives us, that person would make $5,266 a month. If we times that by 12 months, they made, there you go, $63,000 a year. Good for them. Right? So, that's the kind of power that this equation has for us. Letter C here says, the graph shows a collection of data measuring the thickness of the polar ice caps from the past 25 years. Write the equation of the line of best fit. Okay, if you could please go ahead and pause the video and write the equation for the line of best fit right now. So this one should have been much more straightforward than the previous problem because, there's no break in the scale. I'm looking at my data. I'm looking for places where my line is going exactly right through one of these lattice points, little crisscrosses. I found one right here. And then I found one down here. Possibly one right here. Now I want to see if these 3 points follow a pattern. So down 1, 2, 3 over 1, 2, 3, 4. Down 3 over 4. It looks like we have a pattern. Down 3 over 4. Now I should probably check my scales. We'll see, is everything counting by ones? Is this down 3 actually down 3? Yes, it is. So this is counting by ones. This is actually down 3. Is this over 4 actually going over 4? No, because my scale's not counting by ones, it's counting by twos. So I'm going from the number 8 here to number 16 there. That's over not 4 units, that's over 8 units. Down 3 over 8. My slope of this line is -3/8. That's the start of my equation. The only other piece I need is my y-intercept. Now we could estimate this and go, it looks like it's probably +1. We could take one of the points, not the dots on here, but one of these 3 points that I've highlighted, the place where we know exactly the value of the line, and I could plug one of these points in for x and y and find my b value. I could also work my slope backwards. Check this out. If I keep working my slope over 4 up 1, 2, 3, I actually do find that this does cross at exactly +1. Before it was an estimation. Now I know exactly because it follows the same pattern. Down 3 over 4, down 3 over 4, down 3 over 4. So I know it is crossing exactly at positive 1. So there's the equation for our line of best fit. Not too terribly bad. Much easier compared to the last problem. Now I'm going to copy that because I'm probably going to need that over the next few problems. Let's see. Based on the model you made, the line of best fit for or its equation, what is the amount of ice gain or loss in the year 1990? Can I find that from the picture? Well, I'm even wondering, like, how would I plug in 1990 in my equation? Like, what is this x variable? Is this the year? Do I put in the year 1900, like 1990 in here? No. If you check out your variables here, the x variable is the years since 1980. So how many years since 1980 is the year 1990? It's 10 years. So if I take and I plug in 10 for my x variable, 10 years since they started collecting the data. Oopsie, I don't need x. And I now push buttons on the calculator. -3 over 8. Come on. -3 over 8 times by 10 plus 1. I do get y equals -2 3/4. I simplified that fraction in my head. I can tell the little arrow thing means it does simplify, and I can simplify it this way. It is 3/4. So they lost, negative number, they lost 2 3/4 meters of ice. Based off the model, can we predict the amount of ice gain or loss in the year 2015? Now, we would not even be able to do this using our graph. How many years since 1990 is the year 2015? Well, 1990, well, this math is a little backwards, but it'll work out. If you subtract them, that's 25 years difference. 25 years would be like here. This guy would be close-ish, but it's not right on. If we, though, use our equation again, this math becomes so much easier. This is why equations are so powerful in math. It's because we don't need to worry about graphs. We don't need to worry about estimation. All we need to be able to do is plug in the right number, 25 years, in for the right variable, and then use our calculators to figure out the solution. -3/8 times 25 plus 1 is -8 3/8. So they lost 8 3/8 meters of ice. And that's a lot. That's a lot of ice. 8 meters is like 30 feet almost. What would the slope of the line of best fit represent in terms of scenario? So we found the slope. The slope right here is -3/8. What does that -3/8 mean in terms of this ice gain and loss and years and stuff? What does it mean? Can you put a sentence behind it? Can you put a good description behind what does -3/8 mean? And don't tell me rise over run. What do you think? I personally do find it very helpful if I just label my labels from the problem. Understanding that the top number is your rise, it's your y variable. The bottom number is the x variable. So the y variable was the ice gain or loss. Ice in meters. The bottom number was the year since 1980. So that means -3 meters of ice in 8 years since 1980. So even simplify. How about that? -3 meters over 8 years. That I can write a sentence. That tells me every 8 years they're losing 3 meters of ice. That's what the slope is representing. And sometimes if we want that slope as, instead of a fraction like this, if we took -3 divided by 8, check this out. I could say every year the ice goes down by 0.375 meters. Because this slope, the rate here, is how fast it's going down. Well, yes, it goes down 3 meters in 8 years, but if you divide that, it'll tell you how much it goes down in 1 year. In 1 year, it goes down by 3.75 meters. Letter D. The scatter plot below shows the graph of a car's age and its value. Draw a line of best fit for the data. So we want to draw the line of best fit for the data. Now it says here the line of best fit would go through these 2 points. What is the equation for the line of best fit? Okay. So I want you to, well, we can work this one together. You did the last 1 or 2 problems. So let's see here. And if you want to do this by yourself, by all means, pause the video and try it. See if you can do what we got. So the first point is 216,000, which is right there. And then 8 and 10,000, which should be right about there. So my line is about right there. And I'm looking at my line, and there's a pattern I see. Down 1. Oh, that was bad. Down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, and in reverse, up 1 over 2 the wrong way. That alone gives me every single piece of information I need in order to write the equation of my line. Y equals my slope, not down 1 over 2, because that's not paying attention to your scale. My scale here, that y-axis, is counting by 2,000. So that's down 2,000. One box is 2,000 units. Down 2,000 over 2. Simplifying down to -1,000. -2,000 over 2 would simplify down to -1,000. My y-intercept, I can see, looking at the pretty picture where it crosses the y-axis, is the number 18,000. That is the equation for this line of best fit. And I'm going to copy that because I'm probably going to use him over the next few pages. Copy. Now you could have, instead of using the slope to find your slope, you could have used these 2 points and the slope formula, which is m equals y2 minus y1 over x2 minus x1, and said, okay, that's x1, y1, x2, y2. You could have done this to find your slope. You would have got -1,000 as well. And then you could have plugged in one of these points into there and found your b value, but that was so much easier to use a graph. I like using the graph when I can. I only really use the slope formula or plugging in x and y for x and y to find the y-intercept when I have to, when I don't have a good accurate graph. If I'd have to estimate, I'm going to use the equation anyway. Didn't even need the workspace so far. Based on your model, what would be the value of a car that is 14 years old? Okay, well, that's actually going to be very easy now. I want you to try that right now, though. We did a lot of the other ones like this together, but we didn't try one like this by yourself. So if you could, please, figure out the value of a car that is 14 years old. You can either use the graph here, or you can use the equation. I'll pause and I'll let you do the problem right now. Value of a car that is 14 years old. All right. So we see the problem right away is you actually can't even use the graph. Your graph doesn't even go up to 14. It stops at 10. So the equation is your only option, which is simple. You're going to plug in 14 for the year's variable, which was our x. And now we just use our calculator and we go to town. So negative 1,000 times by 14 plus 1,800 should give us $4,000. So a car that is 14 years old is still worth $4,000. That was very simple as long as you knew where to plug your 14 in your equation, the x variable, the y variable. What would the slope and the y-intercept represent in the given scenario? So we want to talk about the slope and the y-intercept. My slope was negative 1,000. My y-intercept was 1,800. Now, that's not what they represent. That's just so we know what to talk about. Slope. Rise over run. My rise is negative $1,000. That's the variable. My y variable is my value, the dollars. My x variable is the age. So negative $1,000 over 1 year. You could probably put a sentence to that. Every year the car gets older, its value goes down by $1,000. Negative $1,000 for 1 year. Okay? And you would probably write that as a sentence. I'm not going to because my handwriting would be very sloppy in this space. But for every 1 year the car gets older, the value drops by $1,000. The y-intercept, also sometimes called the initial value. We saw that back with functions. That is the value of a car that is 0 years old. A brand new baby car fresh from the factory is worth $18,000 on average. So that would be the cost of a brand new car. I'm having trouble slurring my letters together. Brand new car. And there we have it. How much money could you save if instead of buying a new car, you bought a car that is only 4 years old? You maybe don't even need the equation for that. If you understand what this is talking about here, you could do this math in your head very simply. Well, if every year older car gets, it loses $1,000, you could save $4,000 if you bought a car that's 4 years old instead of buying a new car. Just because as the car gets older by 1 year, its value goes down by $1,000. You could also use the equation-y way of doing this, and you can take, and I'm not going to do this, I don't think. You could take this equation, you could plug in a 0-year-old car. We know it's worth $18,000. You could take the same equation, plug in a 4-year-old car. It'd be worth $14,000. And then how much money could you save? You would take the $18,000 for a new car minus the $14,000 for a 4-year-old car, and you get a savings of that same $4,000. Okay, it's different methods. Not one method doesn't work for everybody. So if you weren't able to reason it, you have a backup. You have an equation. All right. Based off this scatter plot, okay, I'm looking at the scatter plot. All right. Which equation below would most likely be the equation for the line of best fit? That's interesting. So there's a couple of different ways of doing this. And I find that a lot of students do this the wrong way, or a way that I would not consider the best way. What I see a lot of students do is they'll go like this. They'll Burrito their data, leaving out this outlier, which is good. You can leave them out. And then they'll draw their own line. And then they'll try to see which of these lines match theirs. I don't really agree with that because first off, you are not a computer drawing your line of best fit. The line you drew almost definitely is not correct. It's probably close, but it's not correct. It's not exact. What I find is a much better method is to actually take each of these 4 lines and graph them and see which one's right and which one's wrong, which one's close, which one's very far away. So like this first one here, I'm going to graph this first line. So it says the y-intercept is 4, and the slope is 1. That is up 1 over 1. So I'm going to go, and I'm looking my scale here. This is counting by 2s. This is counting by 1. So you have to be very careful. It is not up 1 over 1, up 1 over 1. That would be wrong. Up 2 over 2. Up 2 over 2. Up 2 over 2. And I'm going to continue the pattern, and you can see letter A is no good. That is a terrible line of best fit. That is the worst. Well, maybe not the worst, but it's definitely not even close. It's nowhere near where we think it should be. Now we can cross off letter A. Letter B has a y-intercept of 6. Has a slope of up 3 over 2. Now I'm going to have trouble going up 3. Maybe not. Up 1, up 2, up 3 is right about here, over 2. We'll put it right about there. And then I'm going to repeat. Up, skinny line. Up 1, up 2, up 3, over 2. Up 1, up 2, up 3, over 2. Up 1, up 2, up 3, over 2. Erase some of my squigglies, and line. Should be a straight line. Uh-oh. What did I do wrong? So that's a very good sign that something bad happened, because my dots don't form a straight line. So that's a good place to figure out. Let's see what happened. 1, up 2, up 3, over 2. 1, 2, 3, over 2. 1, 2. Oh, I only went over 1. I didn't go over 2. How about that? That looks much better. All right, letter B. How's that doing for a line of best fit? Honestly, it looks pretty good. I'm going to put a circle on it for now. Now, I can't say he's the best until I've checked out the other two, but for now, he's maybe the best. All right, so let's see. I'm gonna go like this. Oops. I'm just gonna take him. I'm gonna save the line in case I want to use it later on. Letter C. Y-intercept is 8. Up 2 over 1. Up 2 over 1. Up 2 over 1. And this is not a good line. Remember, this is up 2 over 1. It doesn't look like it because this scale is counting by 2s. So this is up 2. That is over 1 if you're using your x and y axis properly. So it was not letter C. I'm going to change back to my thicker marker. And then finally letter D. Y-intercept of 5. Slope is 1/2. Up 1 over 2. 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 Line. Terrible. So we have finally narrowed down to which is the right one. It is letter B. That is the best equation, and that is how I recommend you do this. Not draw your own line. Draw the lines they give you and see which one's the best. If you have the option to color code your lines, like I could have drawn this one in red and blue and purple and black, and then have all 4 of them on there at the same time, do that if you can, if you need to. All right, summary. So how does writing an equation for a line of best fit help you interpret and make predictions from scatter plots? Go ahead and pause the video, think about it, and then we'll continue in just a minute. All right, so the way it helps you is, well, the equation is much, much, much more accurate than your graph. We talked about this quite a few times throughout the lesson, where there are times where we would have to estimate from a graph, but we don't have to with an equation. There are times where our graph does not show everything we want. If we want the age of a car that's 14 years old, I can't use a graph, but I can plug in 14 years for my equation. Here, I think when we had to figure out the ice loss in 25 years. 25 years is right here. It's not that dot. It's where the line is right here. I don't know exactly what that is, but when I plug in my equation, I can find it very easily. Okay, thank you so much for watching this lesson on interpreting scatter plots. Until next time, toodles.